Okay, I think we're good. All right, so we've got one more talk of the morning. So we've got an exciting talk by Rohith Kuditipudi. He will be telling us about distortion-free watermarks for language models. So please take it away.
Thank you. Yeah, and I guess we've heard a lot about watermarking, so I'll more broadly talk about our watermark and also more generally distortion-free mechanisms for language model provenance. And the work in this talk is based collectively on joint work with Sally Zhu, Ahmed Ahmed, John Thickstun, Tatsu Hashimoto, and Percy Liang. So get right into it. Behold, the life cycle of a language model. We run some training algorithm, which outputs a set of weights, which parameterize a language model from which we can sample text. And the basic observation that is going to underlie everything I'm going to talk about today is that every step in this life cycle involves randomness. All right, so when we train a neural network, we need to randomly initialize the weights of the model in order to break symmetries. And we typically also do things like run stochastic gradient descent, and sometimes even apply random dropout masks during training. And then, of course, just by definition, sampling is also a random process. And because we have this inherent randomness, we can frame questions of provenance, of verifying provenance, as an independence testing problem. So in particular, if I want to determine if something, like someone else's model, or weights of someone else's model, or some piece of text derives from my model, in principle, I can just run a permutation test. I can resample independent copies of my model weights or text from my model. And if the thing that I'm testing is sort of most similar to the original artifact we released versus these independent copies, then that gives me statistical evidence that that thing derives from my model. It's not independent. And we can quantify this using exactly with like a p-value, right? Of course, in practice, there are a few issues.
Similar data sets?
Well, that's the next slide. Yeah, and as Ankur is alluding to, in practice there are some issues with this. The first is statistical, right? There are unobserved confounders here. So I don't want the power of my test to depend on the training data that was input to this training algorithm. Or in the case of watermarking, I don't want the power of my watermark. I don't want to have to know the user's prompt in order to detect text coming from my language model. The second issue is computational, right? Like certainly in the case of training, it's completely impractical to run training many times. I mean, training a single large language model costs, I don't know, hundreds of millions of dollars. And so, what I'm going to talk about in the remainder of this talk is, well, how do we propose tests for, solving attribution or verifying provenance that get around these two issues of confounding and intractability. Right, and so in the first part of this talk, I'm going to discuss our work with John, Tatsu, and Percy in the paper Robust Distortion-free Watermarks for Language Models. And that's going to be, about how do we attribute text to a model. So as, previous speakers today pointed out, the basic idea of watermarking is that we, the idea is to propose a specific kind of sampling algorithm which then enables us to attribute or to correlate the text that we sample with the randomness that was used to sample the text downstream, all in a way that doesn't require knowing either the prompt from the user or the original language model which generated the text. And so before I go into the specifics of our scheme, I'm just going to describe sort of a high-level abstraction of watermarking and kind of situate and use it to compare our scheme to other schemes. So first, just to recap, I mean, how does sampling from a language model work? Well, we get a prompt and a language model, and the language model takes the prompt and outputs a distribution over the next token. And then we, under the hood, what happens is you get some source or some randomness or some random seed from the computer, pass that through a sampling algorithm, which takes the distribution and outputs a token. And you do this autoregressively for the full sequence. And essentially, the only difference between watermarking a language model versus sampling is that with a watermark, we track the randomness, or we parameterize it using some sort of secret key that comprises the watermark. And so, we've heard about watermarking using pseudorandom error correcting codes. I'm going to rewind the clock a little bit to the state of the world at the time we were working on this problem. And essentially, there was one broad category of watermarks, which I'm going to call hash-based watermarks. And the way these watermarks work is that to determine the seed that you use to sample the next token, you compute it as based on a pseudorandom hash of the previous k tokens for some value of k. And so, one version of a hash-based watermark is due to Kirchenbauer et al., who basically proposed modifying the distribution of the next token based on some pseudorandom hash of previous tokens. Meanwhile, Aronson and Kirshner and Kreis, Gunn, and Zamir proposed sampling schemes concurrent to ours that don't require modifying the distribution of the next token. However, in all three cases, you end up with this trade-off between the amount of bias you're introducing or the amount of distortion you're introducing between the difference between, the distribution of watermark text versus unwatermarked text and the robustness of the watermark. In particular, you can either choose to increase the hash window, which means that you reduce the probability of hash collision. But when you do this, you're less robust, because if someone replaces any one of the previous k tokens or in this hash window, it breaks the watermark signal in the next token. And I just want to emphasize or illustrate that this isn't just like a theoretical issue. This trade-off can manifest in practice. And so here we've implemented like a hash-based watermark where we hash the previous token, and we've queried a language model, Alpaca 7b, to give me a list of 20 movies. And you'll notice like there's a lot of repetition in this list. And one thing I'll caveat here is like, okay, here we're hashing the previous token, just one token, to obtain the signal for the next token. For example, I think Scott would recommend that you hash like the previous, 4 or 5, something like that. And the effect is much less noticeable. But again, like once you start hashing like the 4 previous tokens, you're only robust to, editing like, 25% of the text. So there is this trade-off, and it can manifest in practice. And so the approach we take in our work is to avoid hashing tokens entirely, and try to get around, which allows us to get around this trade-off between the amount of distortion in watermark text and the robustness of the watermark. So the way we do this is that we parameterize a random number generator using a watermark key, and we generate a long sequence of random seeds from this random number generator. And to generate text, we basically randomly sample subsequences from this this code book, and then map these subsequences onto watermark text. And the idea here is that generation is something we call distortion-free, meaning it's indistinguishable from regular sampling of the model until you reuse an element of this random number sequence. And so even we'll get at what the trade-offs are later, but even across multiple prompts, as long as the sequence is long enough so that you don't end up with a collision with high probability, you still have approximate equality in distribution to unwatermarked text. But it does introduce some computational trade-offs, which again we'll get at later. And then to detect the watermark, you just try to align some putative watermark text with every possible code word until you find a good match. And so, okay, that's kind of a high-level overview of what we're doing. But what all the magic happens in how we actually define this sampling algorithm, which allows us to correlate text back to the watermark key. I guess I'll stop here if anyone has any questions. Otherwise, I'll get into how we're doing the sampling.
So
Yeah.
I'm again worried about this issue of offsets. All right, that it seems like if we're just going to use this particular pseudo-random sequence,
Yeah.
in order to do it right, and then what if someone adds a word to the beginning?
You're talking about robustness to insertions and deletions.
Yeah.
So when we do this, when we try to correlate the text to each of these code words, we use Levenshtein distance, and so you get some pretty good actually in practice robustness to edits. I think you can edit 40% insert. Let's say you can do 40% random insertions from I think 35 tokens sampled from llama, and it's
How is
you still
Levenshtein
detect the watermark.
distance different from edit distance?
It's sort of a convex relaxation, I guess, or it's a relaxation that you can compute using dynamic programming. So essentially, what you're doing is saying
You can compute edit distance using dynamic programming.
Sorry, yeah, but like, so essentially what you want to do, right, is say like, okay, like over some edit distance neighborhood, right, of like my text, like, you know, what is and within that neighborhood, what is most correlated with like some code word, right? And the way you can solve that approximately is just using like Levenshtein distance. We'll get into that, yeah. But no, it's a good question. Cool. All right. So how are we actually implementing this sampling? So we do something called inverse transform sampling, where basically like, you know, each element of this like random number sequence is just a number between 0 and 1, which we map to a sample from the language model's distribution over the next token by, you know, I mean, proof by picture. We're just saying like, where does this number fall with respect to like the cumulative distribution function of this language model's distribution. And then we map that onto the next token. And the idea here is that like, okay, as long as like U is uniformly at random between 0 and 1, like this amounts to a valid way to sample from the model. Again, not new, like inverse transform sampling that, you know, widely used. But the key thing here is that like when you do this, and as long as you randomize the ordering of your vocabulary in like a pre-processing step, the index of the sampled token with respect to like this ordering will correlate with the uniform random variable, and you can use this to then like detect text downstream. And so concretely, you know, this detection is just an instance of like a database lookup on a vector database, where we take the token indices of the putative texts and we try to align them with every possible code word. And again, as you know, as I was, I mean, I'm not going to go into the specifics of how Levenshtein distance works, but you can do this in a way that is robust, not just to substitutions, but also insertions and deletions. And the nice thing about like this particular database is that we can generate independent, identically distributed copies of it for free. So even, you know, at the end of this, you get some number which might be uninterpretable, but you can convert it to a p-value using like a permutation test. And then another thing I'll add is like, okay, like, so this is just one instantiation of like the sampling scheme, but you can really, within this broader framework that of avoiding hashing, you can use many possible sampling schemes. So like, as we were writing our paper, we found out that Scott was using the Gumbel trick, and we tried that, and it actually works a lot better in that like you get much more statistical power with the watermark. The only minor like caveat or trade-off is that detection is a little slower. But that could just be due to our implementation. Yeah. So, okay, so watermarking, what works and what doesn't. And, you know, we have a lot of experimental results in our paper that I'm kind of going to skip over in the interest of time, or I'll try to summarize. But at least at a high level, what works about our watermark is that we are distortion-free, as in the sense I've described earlier, in that we preserve the distribution of text and the original language model. And because we avoid hashing, we don't induce this trade-off between distortion and robustness. So we can have this guarantee while also being robust to substantial fractions of like insertions, deletions, and substitutions. But, you know, the trade-off here is that is computation, right? So you can think of what we're doing as like a very naive and maybe dumb error-correcting code, where, you know, the way we do decoding is just using a lookup table. And again, like I said, you know, the amount of distortion we're introducing, it depends on, you know, the probability of reusing an element of this key sequence. And so we need the key sequence to be a number of code words to be very large in order to like maintain fidelity to the original distribution across many queries. But the runtime of detection scales also with the number of code words. So there's this direct trade-off. And so one thing we ask in our work is like, okay, well, can you have all three of these things, right? Can you have distortion freeness, you know, robustness, and efficient detection? And as kind of we've heard about today, you know, in the time since our work, we've had this wonderful line of work on, you know, pseudo-random error-correcting codes where you have efficient detection and also, you know, undetectability. That was sort of originated by this paper from Kristen Gunn. And that's fantastic. The only thing I'll add is that probably there's still more to do here, which is exciting in terms of like, okay, how do you get a system that is, you know, that is practically robust and undetectable or distortion-free, whatever, and has efficient detection, and then maybe the last thing I'll say about, you know, watermarking is that, I've sort of been thinking in our paper, at least, we think about robustness as like, okay, you want to be robust to a certain fraction of like substituting tokens, deleting tokens, inserting tokens. But as Scott and others have mentioned, like, it's unclear if that's maybe the right model of robustness. There's plenty of like very simple automated tricks for breaking all known watermarks currently. And so I think like going forward, we'll need to think about like new models of robustness, and that like what is actually relevant in practice. And I think as others have maybe mentioned, can we have sort of watermarking at a more semantic or conceptual level? That's an exciting direction for future work. But that wraps up the bit about watermarking. So I guess another good place to stop and ask if anyone has questions. Yeah.
How expensive is detection? Is it actually exponential time?
Not exponential time. It's like linear in the length of the. Well, I guess it depends exponential in what parameter, but it's linear in the number of code words, basically.
Okay.
Right. So if you want to frame it as like, okay, you generate this like all code words from like a pseudo-random number generator with like certain that's parameterized by a key. It is exponential with respect to that key size. Exactly. Yeah.
Okay.
Yeah.
But and like what are the constraints on the seed length? Like, could I just take a very small seed and would it still would the scheme?
So I mean, we don't get into the distinction of like pseudo-random versus random. So I don't know like what.
I see.
Yeah.
So basically, when I take the seed to be small enough, then I might give up the indistinguishability.
Yeah. Exactly. But like really, we just think of like this code book, right, as like essentially it's like a particular view of a database of like all possible watermark text you can generate, and like let's just do a lookup on that database.
Yeah.
But yeah, it's parallelizable but expensive, and that's the trade-off. Yeah, good question. Anything else? Cool. Okay. So now I'm going to talk about, doing a similar thing, but now for establishing provenance of the weights of a language model, right? So if you if you're Meta, you release Llama, how can you figure out if someone else has like fine-tuned your model? And this is based on joint work, which is co-led with Sally and Ahmed, and also with Percy. Okay, so I'm going to spend more time on like the problem formulation here, just because, I think we've heard a lot about watermarking, but. And the problem formulation we're interested in is, okay, well, the question is, can a third party infer the relationship between two models from their weights? So what do I mean by relationship? Well, there are a few ways in which two language models might be related. They might be, on the far left, independently trained from different random initializations. One model might be a fine-tune of another, or the two models might both be fine-tunes of some common base model. And what we're interested in specifically is just this question of like independence versus non-independence, right? So we kind of lump the two cases on the right together. We're just interested in testing essentially if these two models were trained from like different random initializations. And that's kind of the problem formulation that we're going to try and solve. And right, so like unlike with the watermarking, in this case, we're assuming that like the person or the entity doing the testing is a third party. So we can't actually modify the training algorithm. Instead, what we'll do is we'll place some assumptions on training that'll allow us to essentially like simulate this permutation testing idea by generating exchangeable copies of the original model. And hopefully I'll convince you that these assumptions are mild, but well, open to comments there. So what are these assumptions? So, well, first of all, I'm going to, for the purposes of this talk at least, think of a training algorithm A as just a map from some initial parameter value to like a final learned parameter value. So completely ignoring or just subsuming things like training data, et cetera, in just the choice of the learning algorithm. I'd say that like a learning algorithm is equivariant with respect to a class of transformations pi, if essentially for any transformation in that class, like A commutes with pi. If we permute or if we apply pi to the original initial parameter, what you get at the output is just the same transformation of the final parameter. And then the second assumption is on the initialization distribution, which is that we assume that like the initialization distribution for the random initialization is pi invariant. And okay, so concretely, like we're gonna think of pi throughout as just like a class of operations that permute the hidden units of like a feed-forward model. And just as a concrete example to illustrate like why basically any training algorithm and most initialization distributions people use do in fact satisfy these assumptions, well, just note that like in the case of a 2-layer MLP where I have like first layer weight W1, second layer weight W2, and that's what my forward pass looks like, and a sigma is like an element-wise activation function. Applying these applying this permutation operation over hidden units doesn't change the output of the model, and all that happens to gradients is that they get permuted the same way. So like when you run SGD or Atom, whatever, you will satisfy this like equivariance property, and this is true basically for like every learning algorithm that people generally use in like deep learning nowadays, and likewise for pretty much every initialization distribution that people use in practice. Because the ordering of this hidden units has no semantics, so there's no reason to initialize them differently. But any questions about like these assumptions? Yeah.
The goal is to recognize the model given the weights even after fine tuning has been done. Or
Yeah.
something like that?
Yeah. Even after a lot of fine tuning
A
is
lot
done.
of fine.
Yeah. Yeah. Exactly.
So clearly some assumption has to be made though about this.
And yeah, these are the assumptions. Yeah. And then hopefully again like pretty much any like But
like this, like this seems like some like equations. Like is there going to be a quantitative assumption about the amount of fine tuning?
No. Well, I mean, we're not gonna.
How could there not be?
We're not gonna prove like with high probability if you fine tune for this number of tokens, you get like this p-value. We're just gonna evaluate on a bunch of models and see like what you get. It's very
So this is an assumption on the training procedure that produces a model that's then fine-tuned?
This is an assumption on the. Oh, that's a good question. So we're running this test between two models, right? We only need to one of the models to have been generated from a training algorithm that satisfies these assumptions. So for example, like we're testing whether someone else's model was fine-tuned from like Llama 2. We just need to, if we know that Llama 2 was produced from like a permutation equivariant like learning algorithm like Atom or SGD, whatever, that's enough for the statistical guarantees to hold. Yeah.
So, Okay. So in this, you only consider fine tuning, or do you consider like quantization, other compression, distillation, other stuff?
Yeah, I mean, it considers an interesting word. Like basically, we make no assumptions about like where the other model is coming from. It's like so again, like Llama 2 versus some other model. Like someone could have done that's just some like arbitrary like I guess random variable, right? And we're just trying to test like is it independent of, say, for example, Llama 2. And yeah, they might have quantized, they might not have even have like fine-tuned, they might have not even have run like gradient descent, whatever. Like, let's just run this test, see what p-value we get out. Yeah.
And then the assumption, presumably if I wanted to avoid this, I could, flip my weights around in weird ways.
Yeah.
It, like you're not considering that. You're just going to look at just like assume the person is doing normal stuff.
Yeah, we'll get to that though. Okay. But that's the elephant in the room is like but I totally agree. Yeah, and we'll get to that. Good question. Okay, anything else? Cool. Okay, and so the reason this assumption is useful is that now I can essentially simulate this idealized like permutation test just by applying a bunch of permutations to the original model to obtain not independent copies, but like exchangeable copies. And so then if someone else, gives me some putative model that was derived from mine, or I say mine, I guess in this case we're a third party. I can compute a p-value by just comparing how similar this other model is to the original released model versus all of the transformed versions. And if it's the most similar to the original, like okay, well that's evidence that it is a fine tune or it is somehow derived from the original model, or at least it wasn't like it's not independent. Yeah.
So for this to work, the only thing that can differ between the models potentially is the weights. Is that correct? Or like
right. So this is like
added a layer that did nothing. Which model would you be able to do some?
So it's a good question, and this gets into I think Nicholas's question as well. Is like what I'm proposing right now is highly non-robust. Like I can, change the architecture by just adding like a single parameter or something. Now the shape of my tensors doesn't match, and this doesn't type check. But we'll get at robustness a little later. But yeah, it's a good question. Okay, but does this kind of make sense? Okay, cool. And then the last thing I'll say is like I won't go into too much detail about like what similarity measure we're actually using to kind of compare these two models, and the reason is just because pretty much doing anything you can imagine like works quite well, like distance between weights, cosine similarity of weights, whatever. And but okay, that brings me to like the empirical validation, right? So basically we tried running this test with like a bunch of model pairs from open weight model pairs from that we downloaded from Hugging Face. And essentially, like in all cases where we know, that the one model is fine-tuned from another, you get like an astronomically small p-value. In fact, like the paper's not out yet. We'll hopefully have it on archive soon. But like our table is basically like every number is just like there's like a epsilon, and epsilon is like below the floating point precision or something. So it works pretty well. And in fact, like to Scott's point, like okay, like how are you placing any? I mean, how robust is this? Is like someone fine-tunes for a while. Like one notable example here is like this model Lemma that was fine-tuned from Llama 2 with something like 30% of the pre-training budget of Llama 2. And like again, still it's just the simplest thing you would try, like L2 distance between weights, whatever, like works quite well. So in some sense the problem is like a little too easy.
I mean, in that case, it would be interesting to know just how much you have to do until it no longer works.
And the problem is we don't have the budget to go beyond 30%. We don't have the budget to go 1% of Llama 2's training budget. But yeah, I guess maybe we could do 31%.
On some smaller model.
And that's a good point.
I'm really curious, given the release of data sets like the Olmo data set and Pythia and all those, have you tried this for just the different checkpoints? Across the checkpoints? Because then you actually have the entire training budget worth of evolution, whether it shows...
It's a good question. We have. There are certain metrics that actually you can correlate the final model with the random initialization. And that like but that's not true of everything. But in general, like all this thing, in general, you can like correlate the last like Olmo checkpoint with something like pretty early on in training.
So you're using L2 distance?
We're using a few things that I sort of like not describing.
Late decay kills L2. You want to be doing something that...
Why don't I just talk about, like, so we do a couple different things. One of which is L2 distance, but the others are which are like, so, you take like the activation vectors over like many like random inputs, and you compute like cosine similarity over the hidden units. You can also do like cosine similarity of like, again, like the attention layer weights or like the MLP weights, etc. They're just, but I think at a high level, just the message is that like everything kind of works.
How you avoid false positives? So
right.
We did several experiments also, like for Llama 3 and Llama 3.1. They said they train from different training data, but the weights is very similar.
So I mean, just the test is sort of like you get control over type 1 errors, like false positives, just kind of like by construction. Well, I shouldn't say by construction. There's an assumption being placed on like the training algorithm, right? But like in the case of Llama 2, like it was trained using like SGD that satisfies our assumptions. So you just like the p-values you get out of this are valid just kind of by construction.
Well, I noticed on the color coding on the chart you showed all the different models. What is it?
Oh yeah, I mean this is kind of just something I took out of the paper. So I don't, but like the different colors just map onto like different clusters of models that are fine-tuned from the same base model.
You can match all of the models within the same cluster to each other, or you try that? Then you red box some of them. Sorry, what is? I don't understand.
I think the red is arbitrary. It's just like another family.
But you can match like all of the llama. Within Llama 2. But then what about like?
Just and then we can match like Granite 7B instruct to like Granite 7B base. Just like basically 2 to 3.
I guess there's a difference in the.
I think we trying Llama 2 to Llama 3 like yesterday or something, ahead of like what we put out in archive. I don't know actually what the result was there. Yeah, we can let you know offline. Yeah.
You plan to try models across different.
I think eventually we want to pull like the top one, it's like 1,000 models from Hugging Face and just like run this and release like some website of like, here's kind of what we found. Yeah. Yeah.
If I develop a model and I want to be able to prove later that somebody fine-tuned my model or something like that.
Yeah.
Could I maybe publish some kind of commitment that is enough for people to verify later that a model was a fine-tune of my model, without that commitment actually revealing a lot of information about what my model is? Like, I don't want to tell everyone what my parameters are.
Yeah, I mean, look, so before I actually answer your question, I'll just say that like in this setting, right, like you're testing between like two open weight models. So in some sense, like, you know, like for example, with Llama, like the weights are already known. So how, you know, like, but you're releasing to run this test, you don't have to release anything other than just like the weights, which you've already released, right? Because like we're a third party here that is like running this test.
But if I have a proprietary model that I want to be able to prove in court later, oh, somebody copied my model, etc. I don't want to release the weights necessarily.
Yeah, and I think that gets at a separate like kind of problem, which is like fingerprinting maybe, or like watermarking, maybe watermarking, but depending on like, yeah. So if you don't release the model, right, then that means you're assuming people are just querying it via some API. And so I guess maybe, are you saying like in this setting, like there's some fine tuning API and you want to figure out?
Let's say some employees stole my model and started their own startup.
Yeah.
They fine tuned my model. So they took the weights, but I don't want to reveal my weights to everyone. I just want to in advance publish, oh, my model has this signature. Anyone can verify later that.
But you're assuming you have access to the weights of like their model?
Yeah.
So this isn't something we do, but we have kind of like in principle, there are some metrics that you can correlate like the final model with like the random initialization. So maybe what you can do is like publish like the seed you use to like randomly initialize your model, and you know like maybe that would work. Yeah.
There's a separate literature on model watermarking methods, and some of them are actually really robust to certain kinds of parameter fine tuning. But you can make a commitment ahead of time if you're willing to make that commitment.
Well, with theirs, but they have this strategy, right, where this like permutation symmetry thing, right? So couldn't you just, after training your model, you know, just permute it so that it has some signal that you want, and then commit to that signal, right? And then if someone else has
it is like trivially breakable. In fact, maybe that's a good segue to get at like the next part of this, which is like how do you maybe so elephant in the room. Like, what about robustness? You know, in some sense, like everything I've talked about is like kind of dumb, like, you know, in any sort of adversarial setting, right? Right, and in particular, it's like very easy to break our test just by permuting hidden units, and this doesn't change like the behavior of like the model at all, for the reasons we've discussed previously. And so then you might ask, like, okay, like, can we design a test with non-trivial robustness? And okay, like, well, what do I mean by non-trivial robustness? I'm not going to like formally define it, but intuitively you can imagine like, okay, at least like at the very least, there shouldn't exist like simple transformations of weights that don't change model output and kind of are uniformly across all models, or like irrespective of the initial weights, but break our test, right? Like at least like that's like maybe the bare minimum that you might hope for. And so, okay, so now I'm gonna get at like our attempt to like design such a test where caveat, like we no longer are able to get exact p-values. I mean, certainly not using like this permutation testing framework I've described, but like empirically it seems to work quite well in a sense that I'll show. So, okay, so in order to describe this test, like you need to kind of get at like the nitty-gritty of like how these like transformer models work and like what the architecture is. So, you know, like one particular kind of model architecture that a lot of these like transformer-based models are using nowadays is that, well, they all, like most of them contain like a MLP or multiple like MLP blocks for the particular type of MLP with like something called gated linear units, which is something like an activation proposed by Dauphin et al. In 2017 and really popularized by Noam Shazir for like language models in 2020. And so the idea, like with these MLPs, so a standard MLP is something we described earlier, is just like you have the first layer weights, the second layer weights, multiply the input by the first layer weights, apply some element-wise activation, multiply by second layer weights, you get the output. And like a glue MLP, you actually just have 3 weight matrices. You have 2 first layer weight matrices, what's called an up projection matrix and a gate projection matrix. And you also have, and then you have 1 second layer weight matrix, which is like a down projection matrix. And so what you do is like, you multiply the input by both the up projection matrix and the gate projection matrix. You apply some element-wise activation function to, and it doesn't really matter what it is for now, but apply some activation function to the gate projection activations, and you take the direct product, and then you just pass it through the second layer weights. I guess I'll just pause here briefly if anyone just has questions about like what a glue MLP is. But the important point is basically like there are many of these, or like 32 of these, for example, inside of like the Llama architecture.
So
Yeah.
intuitively, if an adversary is permuting the hidden layers, right, we just want to just like look at the set, or the list of all the weights, and just see if they match, despite having been permuted.
Yeah. So
Is that what we're ultimately going to be doing?
yeah, more or less. And yeah.
All right.
Yeah. So what is like the actual test we propose if we have like 2, and we're going to propose a test like operates on these MLPs, which then you can apply to like transformers just by applying it to individual layers or aggregating across layers. So what this test is going to be is like, okay, so we're first going to we're going to do 2 things. We're going to like, sample some random inputs, and in practice, like, for this to be robust to like rotating these weight matrices, like X you can think of as like activations coming from passing in like random token sequences to like the input of your language model. And like this MLP is at some intermediate layer of your language model. So what we do is like we pass in like random inputs. We get like a set of activations, gate projection activations for both models and the up projection activations for both models. And then we run some like matching algorithm that kind of tries to find like a permutation pi g that aligns like the 2 models' gate projection activations, and a permutation pi u that aligns the 2 models' up projection activations. And then what we return is like we look at the Spearman correlation of these 2 permutation maps, and then we convert that into a quote unquote p-value. It's not a p-value, it's just a number between 0 and 1. But like we map it onto, we use a lookup table for Spearman correlation to like get a number between 0 and 1 out, and that's like the test statistic. Is that kind of, and again, like there's no reason, a priori you might think that like, okay, well, 2 models might be independently trained, but like deep learning magic, like they might have similar activation. Like there's no reason this test should be like behave like a p-value or have any power, but this is what we try. And yeah, question. So here, like X is like a matrix, so we pass in like n input sequences. Yeah. So I guess like the row, each row is basically a hidden unit, right? And if we pass in n inputs, then it's like an n-dimensional vector. We try to match rows. Yeah, exactly. Yeah. Okay. So again, like this statistic is just like some number between 0 and 1. There's really, there's no like principled reason like why this should like work super well. And because it's just some number between 0 and 1, like this time I actually need to evaluate not just like type 2 errors, but also like type 1 errors, right? I need to empirically validate precision. And so what I plotted here is like we run this statistic on like, I think like 200 like independent model pairs from Hugging Face. And again, this like you can apply it to each MLP block, and there are 32 MLP blocks in like a Llama model. So on the left, I've plotted like, okay, so there's like 200 times 30, basically 6,000 data points in the left plot. And on the right plot, what I've done is like I've aggregated, if we think of them, while we're pretending that they're p-values, we might as well pretend that the p-values are independent across MLP blocks. And if they are independent, then what you do as a statistician is that you can aggregate them using Fisher's method. And that's what I've done, we've done to generate like the right plot. And if this were like an actual p-value, you'd expect these plots to look like y equals x. And like empirically, they do, which is like, to us, kind of strange, but kind of nice. So at least empirically, it seems like this is like, you can get, if you treat this as a p-value, you get like reliable control over type 1 errors. Are there any questions about this slide? Now we can go on to recall. Okay, so now that's precision. And we'll come back to precision a little later on, but now we want to evaluate recall, right? Like, are we actually robust to output preserving transformations. And like the problem with any sort of evaluation when it comes to robustness, like you don't want to get into this like whack-a-mole game, right? Like how do we exhaustively enumerate these transformations? Like I've given you one example, permuting the hidden units of MLP. But like I don't know, like we don't fully understand how deep learning works. Like there might be many degrees of freedom that I'm not thinking of, right? And in fact, like this is a problem that prior work ran into, where they took this approach of trying to enumerate transformations, designing a test that is like robust to these transformations, and we end up showing like you can actually break their test with like another transformation, right? So like we don't want to get into like this enumeration game. Okay, you know, one thing we tried then is like, well, okay, like we have this test that is like running on like the MLP blocks of like this transformer model. Like, let's just retrain these MLPs from scratch by like distilling the original model's activations. And I'm not claiming that like this is like a, you know, the gold standard way to evaluate robustness. Like this might not be capturing something, but at least like you could hope that like when you retrain from scratch, if like there's some degrees of freedom in this model that like you're not thinking about, well, there's no reason when you retrain from scratch that like you would revert to like, you know, maybe you would like capture these degrees of freedom somehow and like break the test. Like that's just the rationale for this experiment. Again, like I'm not trying to claim that like this test is like provably robust because we ran this experiment, but just that's the rationale why we tried this experiment. Where again, we retrained each MLP from scratch, but using like teacher-student distillation. I mean, first of all, before we move on, are there any questions about like what the experimental procedure is here, I guess? If not, I can describe like what the results are. Okay, cool. So like let's say you take Llama 2, right? It has like 32 transformer blocks, each of which has like a glue MLP. And then you like generate a data set to like retrain one of these MLPs by passing in a bunch of like inputs from say like Wikitext or whatever data set, right? Then you cache like the input activations to that particular MLP. You cache like the output activations, and you just like, okay, this is my data set of like XY pairs. And like, can I just randomly reinitialize this MLP and just train on that on this data set? And you know, crucially, like this doesn't require doing backward passes through like the full model. You're just training like a 2-layer MLP, and so it's like pretty fast. Yeah, good question. Okay.
Okay.
Yeah.
Yeah. If it were a linear layer, you would expect to recover the exact same layer with number of
parameters or something. Yeah. Exactly. Yeah. Okay. So we found two things that are at least like so the first thing we found is that like phi, our test statistic, remains like very small even after you retrain the MLP from scratch. Like you could still like very correlate it with the original MLP. And like already like this seems fishy because, you know, if we go back a couple slides, right, like, you know, we evaluated this on like a bunch of independent models, the test statistic was behaving, it was like seemed uniformly distributed between 0 and 1. And so what's the difference between like this setup versus like retraining an MLP like from scratch? And maybe you might say like, well, okay, like maybe the difference is like these independent models, you know, were trained on like different data sets, and maybe like the diversity of the data is like introducing some extra degrees of freedom, you know, and then that explains the difference. And okay, like, well, then the natural thing to do is like, let's just actually try to like retrain at least like a smaller transformer model entirely, which consists of both MLPs and like transformer blocks, self-attention layers, et cetera. Like, let's try to retrain a full model from scratch, from random initialization. And if the only reason we had control over like type 1 errors previously was just because of like the differences in like training data, which all these independent models were trained, then okay, you'd expect that like retraining the entire transformer model, you know, would also lead to like phi being very small, in which case our test isn't valid. But actually, the weird thing is that like when you retrain the entire model, phi is like, I mean, phi is not very small, and it's hard to make a claim about is it uniform because you can only do this so many times. But empirically, it seems like everything is fine, and you know, like this is extremely confusing.
Right.
Yeah.
By small means that they're related to one another.
Yeah. So think of phi as like a p-value basically, and when I say very small, like again, like below like floating point precision, that like small. Yeah.
I think I was supposed to take over as chair, so it's going to be lunchtime.
Oh, okay. Well, that's good because I'm basically done. I'll just say that like one of the goals I think my personal goals in coming to this workshop is that hopefully maybe someone here can help me explain what's going on. I haven't worked on deep learning theory since my time in undergrad, but maybe this, I have no clue what the explanation is here for like why this seems to work empirically. I'll just close there again by thanking my collaborators, and then and then these are the references I mentioned throughout the talk. Thank you.
Okay, questions?
On the 45-degree plot.
Yeah.
What are those dots? Those are individual models. It seems like you have an awful lot of models.
These are model pairs. So you like there's on the left plot, right? It's like number of model pairs times number of like MLP blocks because you can run those tests for.
Get like a dozen models and those all pairs.
I think there are like 200 pairs or something. We're gonna try this with more pairs, before we put it on our archive. But yeah.
Okay, other questions?
In mixture of experts models, do you get like confusion on the directionality of the
We haven't run this on mixture of experts models. I mean, in principle, like this would work. You can run it on like the blocks in one of the experts, et cetera. But we haven't actually done that. But yeah, something maybe.
So whether it's go one way or the other.
One way or the other.
Like provenance is like compare it down to children, like if they have the same weights and architecture, is the expert going to be perceived as a parent?
Oh, yeah, maybe I'm curious. Yeah, maybe we can like, maybe I'll chat offline. But yeah, I'm not maybe fully understanding what you're describing.
Anything else? All right. Well, thanks again.